Okay, in this video I'm going to talk about feedback control systems. So in the previous several lectures talk about the Laplace transform and inverse Laplace transform and block diagrams. So those are very important components to before we talk about the feedback control systems. So now let's do a brief recap of what we talked about in the previous several lectures. So we first talk about how do I use a Laplace transform to convert a system given by ordinary differential equation, let's say given by the input u sub t and output y sub t, and assuming that we have a linear system and given by ordinary differential equation, so we can use a Laplace transform to write this original system into a new form. In the new form, we call it in the S domain. So the input is us here is basically is L of u sub t, and ys is L of y sub t. So this L is called Laplace transform. Okay, so by doing that, so we have the ODE becomes g sub s over here, which can quantify the relation between the input u sub s and the output y sub s. So this is called transfer function. So I also talk about how we could simplify, we could write a complicated system into different blocks. So for example, we could have block here G1s, G2s. So each one can be simple because the block can be very simplified. And of course, those blocks have certain relationships such as a cascade and feedback over here. So this is called block diagram. So essentially, the block diagram, you can write a block diagram as one piece, like a transfer function g sub s. So there are multiple ways we can simplify the block diagram or rewrite the block diagram so we can find the overall transfer function. Okay, so that's essentially we can find the transfer function g sub s. Okay, so once we have the transfer function g sub s and given u sub s, now we can compute the y sub s, which is given by us times g sub s, which gives us y sub s, which is y sub s. So which is a solution in the S domain. So once we have that, we can do the inverse Laplace transform to find out the solution in the time domain, which is y sub t, by using the partial Fourier expansion. So those one you can check my previous videos, talk about how do I find the y sub t, the inverse Laplace transform for a given function y sub s by using partial fraction expansion. Okay, so far we haven't talked about what type of control system we have. We just talk about if a given system and a given input and given output. So what is how do I find the output? Okay. All right. So the next question is, what are some typical control structure? Okay. So we'll now move into a little bit more about the topic, how do we design the control system? Okay. So before talking about very specific control design concept, let's talk about two high-level concepts in terms of control structure. So one is called the open loop control. One is called closed loop control. So the typical control objective, it doesn't matter if it's an open loop control or closed loop control. Our goal is typically given by this. We want output sort of the output to match the input. In other words, we want this y sub t, if I talk about in the previous system, if I give you this ut and yt, I basically want my yt to track my ut. So, but of course, so it doesn't happen very beginning. So the goal is to have yt goes to u sub t as t go to infinity. Or I want to have y sub t minus u sub t goes to 0 as t go to infinity. That's sort of the objective. Okay, to give you a little bit more concrete idea about what this is about, and also to explain what is the open loop control and what is the closed loop control. So I want to give you sort of a very simple example. I hope this is good enough to explain the key concepts over here. All right, so the example I give you is a very simple sprinkler system, assuming that you have a piece of land which have a grass. So you want to control the the sprinkler, so make sure you can water the moisture, the grass, so that moisture level will be at a certain level. So typically this UT is the desired moisture level, so that we can grow, the grass can stay healthy. Okay, so the open loop control means my UT, assuming that this is my UT is reference, remember this is desired moisture level, and this one convert to our control signal. So this is called our control algorithm typically. So the output here, this is my control actually. So it drives the sprinkler. So either turn it on or off, or you can even give us different level of the water output basically. Okay. So the open loop control says the control only depends on the goal use of T, like desired moisture level. Okay, you can set this one. Depending on this one, you can control your sprinkler. You can typically what happens is you're gonna set the sprinkler to start at a certain time, for example, at a certain time of the day, and then stop. It doesn't matter if it's raining or not raining, or it's very hot or not hot. So this probably is not very desirable in practice. Okay. So on the other hand, the second control method is called a closed loop control. So what it does is we still have the goal. Remember, this is still the desired moisture level, and the output is also the moisture level. So we have sort of the feedback, which is called a moisture sensor. We can measure the moisture level and try to check if this moisture level is has reached the desired moisture level. So the difference is, this is called E sub T. The difference is used to drive a control, design my control algorithm, which then give us a control input for the sprinkler, which will drive the turn it on or off, or different levels of water output. So this is sort of a closed loop control. So the control here, if I say this control over here, depends on the goal, U sub T of course, which is desired moisture, as well as the actual moisture level, which is given by Y sub T, assuming here this is Y sub T. Okay, so difference matter, and not just the goal matters, which is quite makes sense in practice. Okay. To sort of give a little more insight about what each of this type of control structure works, so we're going to give you a little more detail about the specific numbers. Of course, the example could be very simple. Okay. All right. So let's simplify the whole stuff a little bit, and assume that the grass, how the grass, the moisture level decrease or increase is based on some sort of dynamics. Okay, this is sort of the dynamics. So also generally we call this called a plant. Okay, you can say any object or any system called a plant, or people call this a system. This is called system dynamics. It represents, okay, if I give a control input, how the system responds to the control input. Assuming here give this a very simple form, it's called 1 over s plus 1. Here I'm using the s domain, okay, not using time domain. Okay, assuming that I can transfer this one in the s domain. Okay. So assuming that here my control is just given by a constant number 2, which means if this moisture level is 20, so this will be input will be 40. Okay, something like that. I just make it up. Okay, don't consider this is the only way or the correct way. Okay, just showing you an example. Okay, and this output is given by Y sub s. Okay, so here this one is also called a proportional control. Okay. Here I'm gonna give a little bit idea about what is called proportional and proportional integral and proportional integral and derivative. This is called P control, PI control and PID control, if you heard of it. So P control basically proportional. What it happens is the control input only depends on what's the output is only depends on the input, and you give a proportional. You just scale up and down. Of course, the proportional can also be negative. Okay. So why this proportional is 2? This is a proportional. This proportional means because if I give you U sub s, so this one here is 2 U sub s, right here. So if I do the inverse of that, it gives me 2 U sub t, which means if my input is U sub t, and here becomes twice of that, yeah, of course it's proportional to what input I have. So this is called proportional. So proportional and integral means if I have something like the 2 plus 3 over s, which means here it becomes, if it's a proportional integral, so this guy becomes 2 plus 3 over s, something like this. So of course you can change the 2 to different number or 3 to different number. Okay, the structure will remain the same. The reason this will give me the proportional integral, because if I do this one, the output here becomes 2 u sub s is 2 plus 3 over s times u sub s. If this will be my proportional and integral control. So here this point becomes this value, which is equal to 2 u sub s plus 3 over s u sub s. If I do the inverse of that, this is what I have over here. So I put it over here, do the inverse. This gives me 2 u sub t plus 3 integration from 0 to t u tau d tau. So this is the integration. Okay, this is the proportional. That's why. So this part, if you use this proportional integral as your control input, you basically will first get the proportional one, and also you try to integrate the input, what input you have. Okay. Similarly, for the proportional integral and derivative, you sort of have a more complicated one, which is given by 2. Okay, let's use a different color. It's 2 plus 3 over s plus 4 times s. Of course, when you have this is my control input, control algorithm. Here, this point becomes it's just this guy times this guy. It's u sub s times 2 plus 3 over s plus 4 times s. Okay, so this is my output over here at this point. This is my actual control. So if I do the inverse Laplace transform of that, so I will get 2 times u sub t plus 3 integrate 0 t u sub t d tau plus 4 times u dot t. Okay, this is what I get. So you have integral, this is a proportional integral, and the derivative. Okay, so that's why it's called the PID control. Okay. Alright, so let's take a look at a simple one. We just have a proportional one. Okay, I'll give you a little bit of summary about what if I have PID control, what will happen, okay, later on. Assuming here my u sub t is 60, okay, just make up this number for the moisture level. Of course, my u sub s is just a Laplace transform of that. It's just given by 60 over s, okay. So, assuming here I use just proportional control. Okay, so the transfer function, because this is cascade, right? Cascade. So y sub s over u sub s is just the product is 2. Is 2 times 1 over s times s plus 3. This cascade, okay? So the output in S domain, like I mentioned, will be just the u sub s times this transfer function, ys over us. Okay, which is u sub s is this. Okay, the transfer function is here. I just put 2 in the denominator, so it's a numerator. So 2 divided by s times s plus 3. So it's 120 over s squared plus s plus 3 divided by s, this. Okay, so this one here, I use a partial fraction expansion. Okay, I don't want to repeat over here, but you can use a partial fraction expansion to figure out this one. So basically, I have s squared 40 divided by s squared plus negative 40 divided by 3, then divided by s squared plus 40 divided by 3 divided by s plus 3. So that's what you have. So once we have that, I can do the inverse Laplace transform, which is the inverse of y sub s is my y sub t. And according to the linear property, so I have an inverse Laplace transform of the individual components. Okay, by looking at the table, so you can look at the table. This here is, you can look at the table. This is the inverse Laplace transform table. You can figure out this guy is 40 times t minus 40 divided by 3 plus 40 divided by 3 times e minus 3t. Okay. Remember here the goal is I want, once I have let's say ut here given is 60. The goal is to drive yt make sure this can reach u sub t as t goes to infinity. If you look at this one, so this is my actual y sub t, and this is value. This guy cannot reach u sub t. U sub t here is given by 60. Over here, 60. Okay. Now y sub t apparently because it's 40t will keep growing. Of course, this guy is constant. This guy will go to 0 because this is negative 3t. T go to infinity, this guy is 0, disappear. But this guy keep growing. So this one never reach 60. It will keep growing. So it cannot match ut. So this one is not, which is not good because it does not match u sub t as t goes to infinity. Alright, so this is just a p control. You may ask the question, what if I have a pi, PID, or PID? Does that help? Okay, so let's take a look at this one. The answer is no. The reason here, I'm going to give you a PID. Okay, you can check PI. Let's assume I have a PID is given by what I just mentioned over here. This is my PID. I just you reuse it over here. So my transfer function, so here you basically replace this 2 by this PID, this piece. Okay, so the transfer function will be, again, this block is a cascade. So this guy times this guy. Of course, I here replace 2 by this one because I'm using PID, not using P anymore. So the transfer function is, this is my PID. Okay, so this is my my system dynamics. Okay, this here is PID. So I do the product because that's cascade, right? So I do the whole product. So and I clean out a little bit. So what we have here is this and this, right? Now I'm going to compute ys. Ys is us time ys. This guy is us time ys divided by us. So this is what us is still 60. So it's 60 over this Laplace transform is 60 over s. Remember, it's coming from here. My us is 60 divided by s. And my transfer function already calculated is just the whole bunch of stuff. So we should just repeat over here. So I put them together. So I have 60 times 2s plus 3 plus 4s squared divided by s cubed times s squared s plus 3. So if we use if I use a partial fractional expansion, so I have, you can rewrite this one as something divided by s cubed plus something divided by s squared plus c something divided by c plus d over s plus 3. If you do the y sub t, because this is a number, I don't want to repeat over here what are these values. So, okay, you can use the method I mentioned in the previous lectures to figure out this a, b, c, d value. Once you do that, you do the inverse of Laplace transform. This is y sub s. This give us y sub t. If you do that, you have something like this. You have a times t squared divided by 2 plus bt plus c plus d e minus 3t. So apparently this yt does not reach to u sub t because this one either keep growing really fast or keep decreasing really fast. Okay, so it never reaches a constant value. Okay, so that's why it doesn't, even if you use a PID, of course you can try PI. PI will do the same thing. It will not give you a desired property, which means yt does not go to et, u sub t as t go to infinity. It does not go to the desired value. Alright, now let's take a look at what is a closed loop control. The closed loop control, what it does is try to introduce the only difference here. So from this one and the previous one, if you look at this one you have an open loop, right? The closed loop is, hey, I'm going to have a sort of a feedback. I'm going to use my actual reading, moisture level, vice versa. I'm going to feedback, assuming here I don't have 1 over here, trying to compare the difference between the desired moisture level and the actual moisture level. So this gives me the e sub t. This is the error, which is the u sub t minus y sub t, u sub s. Let's use it. E sub s, which is u sub s minus y sub s. Or in the time domain, if we do the t domain, okay, or let's say use the inverse Laplace transform, we try the time domain, you have e sub t, which is y sub u sub t minus y sub t. You try to make a difference and use that one to control, to actually adjust your control. You still get a proportional one. So this is my control that I apply to the system dynamic system. Okay. All right. So there's a difference. So this one, but this part I'm drawing over here. This part is called feedback. Okay. All right. So let's take a look at what if I have feedback. What will happen? Okay. So let's first of all compute what is the transfer function. Okay. Because this is a block diagram. So I have first cascade, and I can rewrite a cascade as a product too. Okay, and then I have feedback loop. Okay, let's compute the transfer function. Okay, the transfer function is ys over u sub s, which is this part. Okay, divide by 1 plus this, the whole loop, product of the loop, 1 time 2 divided by 1 2 s times s plus 3. So this is a negative feedback. So you can check my video and pre-video if you have question about why that's my transfer function. So this is negative feedback in the block diagram. So by simplifying a little bit, when you time both the numerator and denominator by s times s plus 3, so I can simplify the whole thing as 2 divided by s times s plus 3 plus 2. Okay, so that's my transfer function. Again, I can compute my y sub s, which is given by u sub s times ys divided by u sub s. So what u sub s again is 60 divided by s. And transfer function is just given by here, we just copy over here, 2 divided by, we write it out with s squared plus 3s plus 2, okay? Which is 120 divided by s times s squared plus 3s plus 2. So I can write this a little bit simple, a little bit more close to the partial fraction expansion, the form, because for partial fraction expansion, I need to figure out the poles, right? So by writing a little bit further, so I have 120 divided by s times s plus 1 times s plus 2. That's what I have. So I can write this one as, according to the partial fraction expansion, this can be written as a divided by s plus b divided by s plus 1 plus c divided by s plus 2. Okay. Now those are just the ways you can compute this ABC value. So I don't want to repeat over here. Okay, this is how we compute ABC value. So we have a is 60, b is negative 120, and b is negative 120, c is 60. So it's 60 divided by s plus 1 minus 120 divided by s plus 1 plus 60 divided by s plus 2. Okay. So once we do that, we can do the inverse Laplace transform. We can find the y sub t. It's the inverse Laplace transform of y sub s, which is also inverse Laplace transform of the individual component. You do the sum according to the linear property of the inverse Laplace transform. So it's L inverse of 60 divided by s plus L inverse negative 120 divided by s plus 1 plus L inverse of 60 divided by s plus 2. So which give us, according to the table, again use the table, we have 60 plus negative 120 times e minus t plus 60 times e minus 2t. Okay, so as you can see, if you have let t goes to infinity, my y's t will be 60 because this guy will be 0. If you let t go to positive infinity, this guy also go to 0 as t goes to positive infinity. So the y's t will go to 60, which means, yeah, it does approach the goal use of t. So this is good, which means the feedback can help us quite significantly. All right. You can also, one way you can do, if you don't want to compute this for all the stuff, all the steps that I mentioned previously, you can also use the final value theorem because you want to make sure the final value will go to the desired value. You can also use the final value theorem, right? Which is the limit of t go to infinity y sub t is limit of s go to 0 s times y sub s. Okay? So once I figure out y sub s, which is given by here, let's just plug in that value over here. So it's 1 s times 120 divided by s plus 1, s plus 2. So the limit, once you compute limit, the limit gives us is also 60. Okay, now let's do a summary about open loop control and the closed loop control. Okay, so the open loop control, typically the poles of the transfer function will always include those of the plant. For example, if I go back over here, if I talk about the plant, my plant over here is I have one s, the poles s is 0 and s plus 3. Okay, so the transfer function, if I look at the pi, okay, if I look at the p control, my transfer function is this. So in poles will be 0 and s is minus 3. So my original system is also includes 0 and minus 3. So it's already over here. And if I have the PID, if I look at the PID over here, if I do a PID, the transfer function is this, right? So you look at this, the poles will be 0, 0, and -3. So it always includes a poles in my transfer function in the original system. So this is what I said over here. So the poles for the open loop control, the poles of the system transfer function always includes those of the plant. However, for the closed loop control, the poles of the transfer function can be changed. If I look at this one, if I use the feedback control, if I look at the transfer function over here, by introducing the feedback, so my transfer function is this, right? So if I look at this, this can be written as 2 over s squared plus 3s plus 2, which is 2 over s plus 1, s plus 2. So the poles become s is -1, s is -3, which is completely different from the poles original system I have. That this one give me the poles are s is 0 and s is -3. However, for the transfer function is totally different, -2. They're totally different. So that's the beauty of the closed loop system, because we can reassign the poles of transfer function. That's also the reason why YT will go to E sub t, U sub t, because we can make it stable, right? We can make sure that this guy will go to this one because I can reassign the poles. Okay, so that's all I have for the lecture.